Well, good morning. We are going to start the morning session with Timothy Porter from the ex-University of West. I don't know what it is. We're going to speak about the space as infinity-groupoids.
Okay. Right. Good morning, and first of all, thank you to the organisers, the organising committee, for inviting me. Now, since it's early in the morning, I'm not going to get into deep formalisms and lots of complicated formulae and so on. What I want to try and do is to look at the question of the relationship between topological spaces and infinity-groupoids. And don't worry, I'm not going to assume you know what an infinity-groupoid is. On the other hand, I'm not going to define it. So you'll see how it pans out. What I want to do is to look at the intuitions behind the relationship, which is conjecture, found, whatever you like to think about, between infinity-groupoids and spaces. And this links what might seem to be very abstract infinity category theory through to homotopic algebra and algebraic topology in a quite classical way. So, if I say spaces as infinity-groupoids, well, I assume that infinity-groupoids, whatever they may be, reflect some aspects of some topological spaces. Now, I have, over the last, well, n years, where n is a too large a number to mention, been very irritated by certain people of a certain school of algebraic topology, basically in the States, who have tended to use spaces in a very rough way. They use it for all sorts of different things, whilst I think of spaces as being topological spaces, possibly with conditional structure. So that's what spaces is going to be for me. Well, what type of spaces do I want to be? I couldn't learn the way how to describe this thing. I got my driving license for this. So, what types of infinity-groupoids? And for that matter, what is an infinity-groupoid? What aspects of a space are mirrored by an infinity-groupoid, and what should be our intuition of infinity-groupoids? My reason for the last question, and none of these questions are going to be answered with a definitive answer. My reason for the last question is that a lot of the time, those of you who work in physics maybe have to read what seems to be a wholly technical paper about infinity-1 categories or infinity-groupoids. How are you to think of these in terms which are nearer to the geometry that you are used to? And I think that's a very important step that needs to be made and is completely consistent with the aims of this meeting. So I want to try and show you that the whole of this machine is very well based on classical questions and classical mathematics. So it's fairly historical for some of the time, and hopefully that will mean that you don't switch off your brains too early. I mean, it is early. Okay, so let's go back, and go back 120 years to 1895. And I won't ask the audience to come out with what 1895 is for this purpose, because we're here. So, Henri Poincaré and his famous papers, which is arguably one of the main bases for modern topology. Now, Poincaré looked both at spaces, and these were typically surfaces or three-manifolds, or what he wanted, and polytopes. And I want to make the distinction because a polytope, or a superficial complex, is going to be a space plus some combinatorial information on how to build it. And that's important, because it's one of the ways that he looked at it. There's another reason why this is important, and that is that if you look at many spaces that arise in modern differential geometry, algebraic topology, and so on, they have got in extra structure. They're coming from algebraic or geometric situations, so are coming with additional combinatorial, often combinatorial structure. So that information also often gets, oh, we will replace it by just its topological space or differential manifold or whatever. It's a mistake to forget where it came from. That's in my opinion anyway. Now, there's a very good, anyone who's interested in looking at the topology, history of topology, there's a very good thick volume, History of Topology, edited by Johann James in 1999, and in it, Sarkadia gave an introduction to Poincaré's work. But I'm not using his thing, I'm using a paper, one or two, by Bob Goma in the Annals of a meeting in Toulouse a few years ago, and he did a very good job of looking at the algebra of paths, which is where we're going to start. Now, according to these sources, Poincaré adopted at least 4 different views of fundamental viewpoint, which I'm going to write as pi 1. Should have been a capital pi, but it isn't. Pi 1 x of the space, and I'm going to use modern terminology, and it's going to be translated into English. So, in no particular order, this first one, depth transformations are covering spaces of x. Now, I will, for anybody who wants to, or wants it, I will give a brief mention of what covering spaces are shortly. There's holonomic groups of an integral connection on a vector bundle. That I'm not going to pick up because it takes me too far away from the other sources. There's the one which most people have met if they've done an algebraic topology course, and that is a set of homotopic classes of loops at a base point or paths, and that will give us a groupoid rather than a fundamental group. And then if x is a polytope, so we've got additional information as a realization of some superficial complex, and again, that I will give some indication of what a superficial complex is shortly. Then we can actually give a presentation of this group or groupoid in terms of generators and relations. And that's a very important third theme that I want to pick up towards the end of the talk. Because that has led to a lot of results in combinatorial group theory. not follow up the second so let's go back and think where Poincaré was coming from. We had, at that stage, mathematics had the use of paths, doing path integrals. There was a certain amount of algebra of the paths. Do first an integral along one path, and then an integral along a path, which you could concatenate. There was also the idea of analytic continuation. And so you had beginnings of covering spaces, dead transformations, which are covering spaces, transformations of covering spaces, leaving the base space. Yeah, is it possible to read it? Yeah, right. Thanks for pointing that as well. So we've got a definite link into parts of classical analysis, which I think is something that we tend to keep in the back of our minds when we're doing things in today, but it's very important for some of the applications of these ideas. The fourth one was this, when we had PhiloQuantumGravity, we got a presentation, which meant that you hopefully could include some of the geometry into the presentation, just as in instance Coxeter groups, the generating elements have got an interpretation in terms of the original situation that they were. So, adding in combinatorial information and how the space was built adds in combinatorial information into how the do is to be presented. And this has a two-way purpose. This is a two-way. Now, a quick recall. I'm assuming that most people have met this. I wanted to put it in because of the fact that it sets up bits of notation, and there's one or two little tweaks that I want to point out, certain special features. So if we've got paths, continuous maps from 0, 1 into x, then we've got a source, which is the evaluation of 0, and a target. We've got composition, there's the usual formula. You go along alpha twice as fast in the first half of the interval, and then beta twice as fast afterwards, and you get a continuous map, which is the concatenation of the two things. We need scale so that it's still fitting in between 0 and 1. But this means the composition is not associative. Write it down. But it is up to a homotopic, and the homotopic is rather important because it's this usual thing. You do one path and then another path, and then you, having considered that, you've got a third one, and you've got alpha, beta, gamma. And when you look at the homotopy, which is written down in all the elementary books on homotopy theory, the homotopy actually happens inside the curve. It really is looking at a homotopy of the reparametrizes the curve in a continuous, deforms the parametrization of the curve to another one. So there's a sense in which it's very thin. It happens within the image of the curve. So that idea of thin is something which comes in occasionally. It's not central, but I think it's something which is quite important. Constant paths act like identities up to thin homotopy. Again, within the homotopy happens doesn't matter about the space. It's all happening within the that tiny bit of the space you're using for the curve. And the reverse paths, i.e., it's my usual thing, you know, so if you've got a path, you've got the reverse path as well. And you've got to be careful, otherwise I'll fall off the stem. So, that again, reverse, showing that it works like an inverse, is up to thin on. Now, even deeper recall of covering spaces. Oh, by the way, I've put a handout version of this, given it to the organisers so that if anybody's wanting to have notes of it, it will be available. So even a deeper recall of covering spaces, and here we've got to put some restrictions on the space. We're going to assume it's connected, just simplicity really, but it gets very messy if you don't. And we'll choose a base point again to keep the exposition reasonably sane. Then there's a thing called, provided the space is nice enough, there's a universal covering space. Now the usual example, as everybody expects me to write down, is if you take the circle, then the real line acts as a universal covering space, and this is all to do with winding numbers and again, back into classical complex analysis. The covering spaces have a unique path lifting property, so that if we have a path, and if we've got a path down in the base, and we've got something in covering space, if you pick a point in the fibre and you've got a path down here, starting at the base point, typically, but not just, then you can lift it uniquely to a path above it. So as long as you say where it starts, it will lift uniquely. And that gives an action of the fundamental view on the fibre. Now, as I said, it's all well known and standard material in a lot of courses on the beginnings of homotopic. Now, the category of covering spaces is equivalent to the category of sets with an action of the fundamental view. And if anybody wants, I can sketch that. But as I said, this is all reminding you, trying to get you to think in terms of these ideas. And the thing is that the fibre over the base point tells you everything, with the action, tells you everything about the covering space. And here we're at Poincaré's deck transformations. Deck transformations are, we've got two covering space, we're looking at automorphisms of the top, which don't shift anything down below. The deck cannot be identical. So this is sort of moving the parts of the pi 1 set around consistently with the projection. And so that was one of the ways Poincaré defined the fundamental. Now, the other thing is that this acts as the key starting point for the definition of the Henri gave. So I think, in fact, he derived it from an earlier one of Sarah, I'm not certain of that, of the fundamental view of a scheme for which there will be meaning schemes as well later. We've had them mentioned several times. So, the algebraic geometry version of that. And here the interesting thing is, this is related to Galois and the famous SGA1 seminar, which defined the fundamental scheme. So, this Galois Poincaré mix is one that will come in later slides. Because we're still at dimension 1, and actually, although here we're now back in the probably 1960s, but we're still in 1895, so I'd better get on otherwise I'm not finished. Right, simplicial complex. I said I was going to give you a brief reminder of that. I'm not going to define it, but think of the space as having the sort of thing you see in computer graphics, you know, dinosaurs with wire frames. And that will give, if you don't know the definition, that will give you enough to go on with. You can form a span skeleton, I don't mean a dinosaur skeleton. The one cells of the one synthesis of the simplicial complex. You form up the 3-groupoid on this. It's enough just a graph, just of vertices and edges joining them. You form the 3-groupoid on this, and then whenever you see a 2-simplex or a triangle, which I'll call V0, V1, V2, you force the path that goes round the two sides of it to be the same as the path that goes along the bottom. So you're adding in these relations, and that's how you get the bit. This one is correct. The other ones were meant to be capitalized. So this is how you get the presentation. Now, as I said, these ideas were later taken up by Schreier, Nielsen, and others, and formed the basis of a lot of results which anyone has now called combinatorial reducing. So, results on presentations, results on 3 groups, Nielsen Schreier theory, all relate and come out of this sort of way of looking at things. That is a point I want to suggest is one that could be important. Right. Now, I leave the 19th century and I come into the middle of the 20th century, and one of the beginnings of modern homotopic. The quotes I want to take come from Henri Whitehead's ICM address in 1950, and he talked about an area which he wanted to develop, which he called algebraic homotopy. Not homotopical algebra. And here's the point actually. I could have talked a lot about homotopical algebra, Green model categories, etc. But it gets technically quite hard fairly quickly, and you've got to go a fair distance before you get some beautiful results, but they're a bit more tricky to approach. So I'm going to come at it from a different level. Whitehead said the ultimate aim of this algebraic homotopy is to construct a purely algebraic theory which is equivalent to homotopy theory in the same sort of way that analytic is equivalent to pure projective geometry. This is quoted in Hans Bauer's book, which has got the title on it. Now, a statement of the aims of this algebraic homotopy might be the following classification problems, the homotopy classification problems. Classify the homotopy types of polyhedra, i.e. polydose, realizations of solution complexes by algebraic data. And then compute the set of homotopy classes maps in terms of classifying data for x and y. So, we've got an algebraic model for x and an algebraic model for y, and we want to be able to work with it. Maybe it's totally unrealistic, but when is it realistic? When is it not realistic? When it's not too realistic. And the points to note are that this sets up, 1950, the set of modeling nice spaces by algebra. Modeling them quite completely as far as their homotopy. But does not make any claim to know what algebraic data is to mean. He doesn't actually seem to know what algebraic might mean. And that is an interesting point that I think we'll pick up again later. Each such context of algebraic homotopy clearly requires one to model not just spaces, but maps. And sometimes we tend to forget about this, and I've actually had left papers where somebody had come out with what was going to be a beautiful model for a homotopy type, or a strictly class of homotopy types, and never actually checked factoriality of their constructions. So doesn't know how they're going to compare homotopy types if they haven't got any maps to do that. But it has to correspond in some sense to a function. Now, it's interesting, Henri Whitehead, 1950, was already using Catren language. He had picked up the beginnings of category theory and seeing the usefulness of it. But here we've got, if we've got such a thing going from the top, a category of suitable spaces to algebraic data of the type unspecified, we've got immediately some notion of a weak equivalence coming in, which is, I'll call it an F-weak equivalent, because F is going to depend on that. It's going to be those things that we become isomorphisms when we go over together. So things that our models can't tell the difference between those spaces. F is an F-weak equivalent, little f is an F-weak equivalent of x and y, then our models can't tell the difference between x and y. So, I'm not asking for a complete solution to all the problems. I'm looking for instances. I mentioned this. If I was to go on with this, it would be good to talk about model categories. But I'm not going to. People need a course in that. I remained half an hour. Just have gone through my slides here actually. Particular format doesn't actually help me. Okay, let's look at some examples. Now, the classical case would be, the algebraic data would be a the list of homotopic groups. Okay, that would be a very simple example. So all the homotopic groups mapping the spheres in your space at the base point, and giving homotopic classes of those maps gives the fundamental group and then a whole lot of abelian groups, and we can look at that. We could ask for, well, there's an action of pi 1 on all the other homotopic groups. We could add that in, so that's another bit of additional algebraic data. Or we could add in, well, there's a lot more actions, there's a lot more operations around. And if you do that, you get things which are called pi algebras. But very interesting, they've got a lot of structure. Now, you might say, well, he's forgotten to talk about infinity-groupoids. Well, I haven't, but you'll see that coming in shortly. But the relationship between this approach and the infinity-groupoid approaches nowadays, I think is an area which needs to be clarified. There's got to have to be some linkage between the two sides, you know, algebraic homotopy theory, and then the infinity-groupoid machinery. There's some interesting problems there. In this case, weak equivalence is just a classical weak equivalence. It means you're getting all the homotopic groups are the same, and the map gives you the isomorphism. Notice it's a question of the homotopic groups are the same because the map is an isomorphism. They're same. Now, that's an important consideration. N-types, that is the case where you're just looking at the homotopic groups up to and including level n, have been introduced in 1941 by Fox, and Whitehead picked them up in 1949 and started talking about them because 1949 is a very famous date for Whitehead papers. It's famous date of combinatorial homotopy 1 and combinatorial homotopy 2, and this is when CW complexes were formalized, which are a generalization of simplification complexes, if you have that. Right. You could also work with the algebraic data being pi 1 and the homology groups, and the general homology group is where you don't need to just accept it, of the universal cover. The homology groups of the universal cover are together with pi 1. The F weak equivalent is identical to the weak equivalent. And then you can take the fundamental complex of F. I have to mention this, with Bangor and line down. I've got to get the plugs in. Fundamental complexes, when you're taking CW spaces, again, these are spaces where it is known there is a CW complex structure. The structure is not specified, it's just known to exist. If you pick one, you are making a choice, and that's a very important idea. A specific CW complex is not necessarily given just the existence of one. Now, algebraic models for two types. I mentioned n types, so this is just ones we've got pi 1 and pi 2. We couldn't care less about any of the others. They're not really in our model. We're not asking for an enormous machine which is going to get us all the information stored, just pi 1 and pi 2 and enough information to get things back. But I'll assume that I've got a CW complex structure on my space, so this here is the one skeleton of my CW complex. Pi 1 of x1 is a C2. It's, remember, the point of the superficial complex, that generalizes. And then this is the relative homotopic group of x relative to its skeleton. And this gives a free strict R to the volume. So it's taken me half an hour, a little bit more, to get from Dukes to 2 group I. That's still going to get all the way up to infinity, so I probably will have to go fast. So I get it. So I get it. This is in fact a cost module. This is in fact a cost module. It's a free cost module. This is a free strict. And this is a free strict. Strict. Oh, well, I haven't mentioned that. That's going to have to be looked at. But I'll wait for it a little while. The cross complex I mentioned, and then it's fully explained in a big blue book of Ronnie Burns, this is really a chain complex with a cross module at the base. Let me just say what I mean by that. You've got a chain complex, so you've got a whole lot of abelian groups. But when you get down to the bottom, you've got C1 down to C0, and I'm in a connected case, so I assume I'm working with groups. This is a cross module. All the others are just the usual things in the chain complex where you've got delta delta being 0. And there's a whole lot of conditions about the action. This group here acts on everything above it, and it models a fair amount of the homotopic type. It is equivalent to a strict homotopy. But the important thing is it's strict. Now this isn't good enough, in fact. It doesn't model all the homotopic type. But it does it's a step in the right direction. And another way of looking at this, in fact, is due to Jean-Luc when he looked at n-types, and he looked at what's called cat n-1 groups. I would say groupoids, it's fairly easy to extend it to groupoids. These aren't heading off in n categories. Now, an n category is something where you've got objects, arrows, 1 arrows, 2 arrows between 1 arrows, 3 arrows between 2 arrows, 4, well, I will announce my spatial dimensions, so I can't wave my hands in that way. So, instead of that, this is an n-fold groupoid. So, you've got n different category structures, n groupoid structures, all interacting in a very neat way. Perhaps I should say the usual thing about cross modules. A cross module is a generalization of a normal subgroup. It's a normal subgroup which isn't a subgroup. That doesn't make sense, but it does. Cat 1 groups are the same as, really the same as cross modules. Cat 2 groups correspond to a group and 2 normal subgroups being specified. No prizes for guessing what n groups are. Right. I think that's the end of my algebraic homotopy. Oh no, aside on cross complexes. Cross complexes give a sort of linear model of homotopy types. They include all the information on the two types. This is a quote, by the way. Although they are not the most general model by any means, they do not contain quadratic information such as Whitehead products. And remember, I said strict Homotopic, strict infinity-groupoid earlier. These cross complexes associated there. This question of Whitehead products relates to the fact that you can't get away with strict infinity-groupoids in higher dimension. So this old idea of Whitehead products in the topological case corresponds to things which are causing a weakness, a weak n category, like a monoidal category or the Poincaré categories we saw yesterday. Now this simplicity makes them easier to handle and to relate to classical tools. But I won't bother with that. Now there's a problem. I said, suppose we've got x and y are related by a weak equivalence, classical weak equivalence, and the homotopy groups are the same. Now suppose you've got two groups, two spaces, and the homotopy groups are the same. Are they weakly equivalent? And it's not obvious, because, okay, you may have a, I said they were the same, so suppose we've got the homotopy groups are the same, and the actions of pi1 in each case correspond via an isomorphism at all levels. Is this enough to say that we can build a space? A map between the spaces which induces this map? No. There is a realization problem. There is a problem of actually coming out with, given the models, this is a question of whether the modeling process is full, essentially, full at a homotopy level. Now, there are cases where it works. I mean, if you look at this, the CW complex of dimension k, then its universal covering space is, and so that when you look at the chain complexes you can use for defining its homology, there isn't anything above dimensions k. And Whitehead used, in his original 1949 papers, used this to solve the realization problem for three-dimensional polyhedra, which meant that he could get a complete description. Now, I'm a bit fascinated, but when we get on to, towards the end, to infinity-groupoids, there's very little explicit linkage between the geometric dimension of a space, if it has one, and properties of the infinity-groupoid. I think that's, it's not that it's important for applications, but I think it's important for the intuition and the understanding of how this fits in with other cases. So the three-dimensional polyhedra case works. You need a lot more to make the four-dimensional case work. Right. That, I've forgotten about these last two slides. So now I want to go over, skip up to pursuing stacks. Here is beginnings of a long quote. I won't read the whole of the quote, but it's from Gerstenbeek. Running around at Bangor had sent some of his preprints on cross complex and infinity-groupoids and things like this to Grothendieck, and Grothendieck was spurred to ask Quillen, who never replied, I think, what he thought of this, of a wider attack that Grothendieck had thought of in some letters to Larry Green, which we'll see shortly. This is directly relevant to the question of spaces as infinity-groupoids. Now, what Grothendieck wrote is that he thought for a moment that what Ronnie Brown had done at Bangor had answered the question he had, but then he realised it wasn't going to do that. Here you are. Let's see. I'll leave it. At first sight, it seemed to me that the Bangor group had indeed come to work out quite independently one basic intuition of the program I had envisaged in those letters to Larry Green. This is a quote from an earlier paragraph which mentions this. Namely, the study of n-truncated homotopy types of semi-simplicial sets or of topological spaces was essentially equivalent to the study of the so-called n-groupoids, where n is a natural integer. This is expected to be achieved by associating to any space, say X, its fundamental n-groupoid, pi nx, generalizing the familiar Poincaré fundamental groupoid for n equals 1. The obvious idea is that zero objects of pi nx should be points of x, one object should be homotopies or paths between points, two objects should be homotopies between one object, etc. This pi nx should embody the n-truncated homotopy type of x in much the same way as for n equals 1, the usual fundamental groupoid embodies the one truncated homotopy. He then discusses the fact that weak infinity groupoids were needed, basically because there wasn't composition wasn't associative, the other things were not on the nose, they were going to have to be taken into account. So we got this now in 83, and I wrote back to Grothendieck and I said, well, your infinity groupoids, surely there's a very good model for them, and that's Kan complexes, which are a particular type of simplicial set. Simplicial sets generalize simplicial complexes. A Kan complex, well, let me just give you, if you've got a horn, which is a collection of simplices which of a given dimension, here is n equals 1, that fit together as if they were parts of a higher dimension, one higher dimensional simplex, minus one face and the interior. So you take your simplex, a big simplex, an n plus 1 simplex, you scoop out the middle through one face and throw it away. Now, if you're going into a Kan complex, then there's a way of extending this map. So this is a family of simplices in here. You can extend it to a map from the whole of two simplex in this case. So when you can do this for all horns, then think of a Kan complex. Now, why is this important? Well, if you look at mapping those two edges in, well, there are two paths. Now, into a space, map this into some space X, we found out how to compose earlier. What you do is you take a 2 simplex, which has those two edges on, you map that in by, first of all, mapping it down onto this part. So you just squash everything back into the horn, squash it up, and then map that in. And that gives you a map here from the whole of the 2 simplex. But you've now got 1 simplex along the edge, and what you find, if you choose the right squashing, you get the formula for alpha dot beta that I wrote down earlier. Yes, this one's thin. It depends only on the values that you've got on the horn. So, what I suggested, whoops, I forgot about to say. What I suggested was that because of this fact that you had some sort of composition available, that this meant that, Can complexes already had a lot of the features that Bernoulli was wanting for his infinity-groupoids. He came back to me the next letter and said that the singular complex structure wasn't what he was looking for 2 reasons. That the simplicial sets are not globular, unlike the intuition of higher categories, and then the composition is not defined precisely, it is only defined as the homotopy. I deliberately chose to come up that way. Why didn't I come up like that, or like that? There's lots of different choices. Any 2 of those choices are homotopic. They're all thin. So you can counter these, and for this, George Martiniotis and various other people have actually taken the ideas behind Bernoulli's construction and worked out a globular method of doing things. I can't help feeling that there's a point in actually looking at this notion of thinness and trying to see if one can make sense and make the model coming from the Can complexes, and in particular the singular complex, a little bit stricter. So using some ideas related to the complicial sets that Dominic Verity has come out with. So singular complex gives you some idea of what an infinity-groupoid would be. But it's not the end of be all and end of, because it's still way back in classical algebraic ecology. This letter to Quillen has led to some people using the term homotopy hypothesis for a related idea, but then I don't really think Bernoulli didn't say the homotopy hypothesis. He was actually saying, if you have a notion of n-groupoid, this is what we wanted to do. If you have an n to the infinity. So, what is the homotopy hypothesis, as it is called? That there is an equivalence of weak n+1 categories between spaces up to n homotopy and n groupoids up to n+1 equivalence. Now, there's a lot of terms here which I haven't defined. good. People define them either. So I'm in good company. The challenge in any given setting where you've got an idea of algebraic data is to come up with a notion of n category and also n groupoid that passes this test. So this is one of the things that if you are looking at spaces as infinity-groupoids need to be able to pass this test. If you've got a notion of infinity-groupoid, this is one of the litmus tests that you should do. I'm beginning to run out of time, so let me just go quickly. Can complexes do handle things well? So there is a weak form of the homotopic hypothesis, and that's classically true. Can complexes aren't algebraic enough. I think that that's fairly obvious. You can do this in various ways and make them more algebraic, but it's always going to be feel a little bit artificial. One way that you can, another sort of way you can use, instead of sort of picking fillets for all horns, is you freely adjoin fillets for all horns in some sense, and then you've got, in a particular sense, and that is to form what's called simplicity enriched groupoid. And that gives you formal compositions of parts, and then you pair the formal compositions with the geometric compositions. That works well. You get simplicity enriched groupoids, and you get a very nice functor W bar, which takes you back to simplicial sets, and in fact can complexes. So, based on the fact that these can complexes form a good setting for doing things, then you can go further. And this is all classical in the 1960s classical algebraic topology, simplicial algebraic topology. W bar G gives you a link with principal G bundles and therefore with the covering spaces. I'd like to get very quickly onto that. Grothendieck was referring to a letter of dream. And I'm not going to have time to read all of this. So let me just point out, I've put some parts in blue. The points in blue are the ones that I want to emphasize. There's a notion of an n stack, which is like a sheaf of n categories, or n groups. And Grothendieck was trying to get a local description based on something that Artin and Meza had done, and that's the Italian Homotopic lecture notes, string lecture notes 100, which measured that. This one is a bit difficult to understand, but it's the first of three. If you I'm going to go to C because I'm running out of time. The n minus 1 stacks on X should be able to be identified with the n functors from the category Cn, which is n groupoid, to the category n minus 1 cat of all n minus 1 cat. Remember that if n is, if we're looking at the covering space things, we're getting pi 1 sets. Pi 1 is a group. Sets are 0 categories. So the next stage up should be a pi1, a pi2 2-groupoid acting on one categories. Then you should get a pi3 3-groupoid acting on two categories, and so on. So this is a direct generalization, and this point is made by Grothendieck. In the case n equals 1, this is nothing other than the Poincaré theory of classifications of coverings in terms of the fundamental groupoid C for X. Now, I think I'm going to stop there because I've used up more or less the hour, and I haven't got time to do the last thing, which is to look back at the link with combinatorial group theory.
You can take 5 more minutes.
Oh, right, okay. I'll just do it a bit too quickly then. Right. But notice we've got the way that Grothendieck had introduced this, well, going back to the title, spaces as infinity-groupoids, or spaces up to n homotopy is n-groupoids. That reflects very much on both the paths version of the fundamental groupoid and the covering space theory. So both of those are essential for this new way of 1895, it's not, but you know, that. So already in Grothendieck's letter to Larry Bean, there was this was being pointed out. And of course, there's a lot gone on since then, and I'm not going to try and mention it. Right, that's just a brief thing about the very recent papers have actually looked at the sort of a Galois theory interpretation of this in the last couple of months. So that's what this second thing is. Right. Okay. Theme 3. I said when we came to right from the start, I said there was this link with combinatorial group theory, and in fact, when we get to we had this thing about if we had a CW complex, we could build a thrust module, which is a 2-groupoid. But if we change the CW structure, we've got to change the presentation. So, changing the CW structure, changing a presentation, well, it's pizza transformations and all the rewriting ideas of combinatorial group theory. So, if you try and do this with the CW complexes, there's an interesting thing that happens, and again due to Henri Whitehead, and that is, it doesn't work. And in other words, there are spaces where you can't realize homotopy equivalences between two spaces, or in terms of doing something to the structure. You can't, it's called simple homotopy theory, and you find that there are spaces which, when you look at them and try and realize a homotopy equivalence by, say, adding in cells and then squashing other cells, never changing the homotopy type, adding in things, squashing them down, expanding, then contracting, then you can't realize all the homotopy equivalences using these combinatorial ways. Now, the reason why this is interesting is that's one of the two bases of algebraic K theory, and it's another question, another history completely. But here, what about doing this for infinity-groupoids? If we've got our favourite definition of infinity-groupoid. And I come up with another version which uses some CW structure, some combinatorial structure, to build myself a smaller, hopefully. I mean, some of these models are enormous, so I want to be able to handle it. I really would like to be able to do that, to replace, by using combinatorial information on how a space is built, and not all spaces are holotopes, of course, then I would like to be able to build a smaller model of my infinity group. Now, this is possible up to a point, but this would need a combinatorial infinity-groupoid theory to mirror combinatorial homotopic theory, and it doesn't exist as yet. So that's a sort of, in some sense, a challenge to anybody who's looking for a nice way of understanding infinity-groupoid theory. It's to sort of say, well, okay, suppose I've got additional information. How can I build something which models this big infinity-groupoid by something slightly smaller, using the combinatorial information? Conclusion. Right. I think it's simplistic to say that spaces are infinity-groupoids, or infinity-groupoids are spaces, because we're forgetting too much of the different rich structure that spaces have. But spaces can be modelled, or paths and higher dimensional analogues of that can be modelled by infinity-groupoids. That is the modern, I hate that word, it goes out of date so quickly. But it's the modern way of looking at the extension of the path algebras, of taking paths, integrating around them, looking at connections on various geometric situations. All that, we've got this infinity-groupoid structure reflects that. But there are also, there's also the covering space picture, and that again is a very useful structure, provided we don't take it too simplistically. So I'm trying to get people to stop using space as a term for an infinity-groupoid, because it just doesn't seem to be. It's not spatial. I mean, it's anyway. Something that irritates me. And then, of course, there's this hole in the theory, which I think is this question of a combinatorial theory, which is the third of Poincaré's themes that I picked up, which hasn't been developed. And that's, the rest of it is some thing. So.
Thank you very much for very clarified. So my question concerns Grothendieck's objections to the project. And first, is there any, say, argument behind, perhaps explicitly, or perhaps you may reconstruct it? I mean, like pro-global approach versus simulation.
In Grothendieck's letter, he, in his reply to me, he said, when you actually meet, say, 3 groupoids in the street, I mean, you didn't use this, when you meet them in real life, in algebra, and for him that would be the algebraic geometry, then the things are globular. Therefore, he wasn't satisfied with the simplicial picture. He said it's forcing a beautiful globular situation into something which is maybe combinatorially very nice, but it doesn't have the same feel. And it's really at that level that he was okay.
So there was no
And he also it's feel. I mean, but that's, we've got to have intuition, otherwise we can't. If you force your intuition, and this is very philosophical, but if you force your intuition into the wrong form, you can't push it forward. It's got to, your intuition's got to reflect things. He also said that, I can't remember the exact quote, and it may be in Pursuing Stacks, that he thought that there would be as many models of infinity-groupoids as there were mathematicians working on infinity-groupoids.
But do I understand also concerning second objection you mentioned? Do I understand correctly that's actually part of the first, right? So he wanted a weak groupoid. So strictness in this context just means strictness of composition, and that
he wanted strict composition because he wanted to think about this. But I mean, you can always pick a composition, and then that's fine. He was wanting to. This already occurs in bicategories. I mean, there's various ways in doing the first weak 2 category structure, whether you actually require a composition, a strict composition, a composition map, or merely, and if you go into the algebraic topology, you've got, I'm on thin ice as far as my knowledge, my detailed knowledge of this is, but you get situations where you get the possible, that there is the set of possible compositions is contractible, sort of thing. But you don't want to choose one. Because if you choose one, you're losing what you gained. But, it's swings and roundabouts. As is the question of the globulars against simplicial or any other. So the marvelous growth of models of infinity categories, infinity groupoids, is a reflection of this. And they reflect different aspects. And as long as they're equivalent, that's a great richness. So.
Well, I thank you, Tim, for your very enlightening talk. What I would like to make is 2 remarks. One on the very start of your talk, and one at the very end.
He went to sleep in between.
So it's a remark for all your talk. The first remark is when starting, you insisted on the fact that the importance of starting with some combinatorial extract data on your space, and also on the fact that the space has to be locally nice, and perhaps I would say locally known. So, just on this point, perhaps the young people have forgotten what is written in Chevalet's book. The presentation of coverings in Chevalet's book was very enlightening for me. It was 6 years ago. You know that Chevalet doesn't start with paths. He starts with chains of open sets.
Yeah.
And it's very combinatorial and also very adapted to space which are locally new and to spaces which are what would I say? Locally nice, I mean, and also to spaces like manifolds, conditions, and things like that. Well, now, so it's about the combinatorial aspect, which is more evident than perhaps when you draw paths. It's less evident that it's combinatorial. But when you use chains of open sets, it's clear that it's purely combinatorial data. Well, the second remark is about the end. Well, it would be completely informal if I was able to do what I'm going to say. I would have done, and just a very little part. But what I think is that the geometers are able to do some little part. So the remark is, of course, we observe that to go to infinite, you have to be able to go from n to n plus 1. And so you have to know what happens at the step n, and then you want to go to the step n plus 1. And for going from n to n plus 1, you have to be able to go from 0 to 1. But of course, if you start with a space which is very, very, very simple, it's not so difficult. But I think that sometimes, now if you want to go to n to s plus 1, n may be rather intricate. It is, but it's supposed to be null. So I have an example from geometry where we are able to start to go from 0 to 1, but 0 is rather intricate. And this example was known by geometers, Henri, Van Ness, and people like that, when they define the fundamental group of the quotient space of evaluation. And so observe that especially it's evident in the construction used by Van Ness that it amounts to be able to say what is the pi 0 of a groupoid with a certain structure. So, and the step from 0 to 1, in a certain sense, is a way to associate to this groupoid for 0 to a groupoid for 1. I cannot be more precise. But so what I would like to say, pardon? Oui, no, it's that you I've forgotten what I wanted to say. So in 0 you have some information, and the construction used by Van Ness enables to go to the step 1. I cannot be more precise. I've written a note on that subject, and of course it would be very interesting. So the idea, the link with various structured groupoids is that at the step 0 you have a groupoid with a structure which we describe the structure of the step n. And so you would like to have a deductive process. Well, I don't know what I am able to do that, but it's possible from 0 to 1 for relations. It's just one.
I think there's on your earlier point, if you look back to this, if you look at the letter to Larry, Bertrand is talking about mapotoposes, and in fact, if you look, this whole business there relates to approximating spaces by hypercoverings, and so this part here actually does relate very closely to your first point about looking at chains within covers. So, I mean, and the second point, spaces as infinity-groupoids. Spaces aren't the end. One should be looking at n stacks to start with as honest geometric objects. And that relates to your second point. So, and I think that's going to come in various other talks as well. So.
Any other question?
So my question would be, do you think that infinity groupoids can somehow have an application or can be used in physics?
I think that specific classes of infinity groupoids are already being used in some parts of theoretical physics.
Okay.
But a lot of the time, historically, remember I said about chains on the universal cover and the action of pi 1. Well, that's handling classical homological type things using chain complexes. If you go from chain complexes and bring in a bit of a groupoidal structure, you're beginning to already get to situations which are still sort of fairly linear, but are like Mikhail's Picard n categories, and so on. So it's happening. Whether it will solve anything in physics, and how do you think of them, that's, in some sense it's not, as a mathematician, I think, oh, well, I've got a certain intuition of physics. And of course, physicists have a certain intuition about mathematics. And, well, it's trying to match them together so that, in fact, there might be, whether it's going to do something useful, but it'll be very interesting. So, useful is always because you can have something that looks absolutely useless now, and in 20 years' time, somebody suddenly says, "Oh, just what I needed." So, I would hope there was, because there's a lot of structure where you've got that sort of picture.
Well, I have just a small question about a canonical description in terms of homotopy groups. Like for infinity algebras over here, one can make really canonical description of the minimal model of differential zero net and two discrete satisfies an axioms and depth of motion in model. But is it possible to do something combinatorial for homotopy? Just take these sets pi 1, pi 2, and so on, and get some auxiliary multiplications which will describe some axioms and describe the structure.
I believe it is, but I don't know how to do it. Because there's Hans Bauer has tried to follow up in this. That he first of all looked at the basic way of extending some of combinatorial homotopy theory from Whitehead's 1949 papers to higher dimensions. And in here, in the combinatorial homotopy in four-dimensional complexes, he talks about trying to get a sort of a minimal model from a four-dimensional polyhedron. He's having to bring in more than I've introduced because you've got quadratic complexes where you're actually just allowing yourself to get, well, the interchange law in the infinity-groupoid isn't working. So you have to put something in there. You've got to sort of use, you have to have an interchanger using the way that John Byers keeps on introducing terms. So this relates very closely to trying to understand the relationship between the classical non-stable homotopy theory, operations and so on, with the infinity-groupoid structure. And it also relates to this lack of a combinatorial infinity-groupoid structure. I don't know whether that answers your question, but I mean, I didn't mention the questions relating to minimal models and that sort of thing, because it would have, well, you saw I had to increase speed. I was trying to get 120 years into an hour, so.
Any other questions? So we can have a talk.